recording. So the aim was to join up a little bit with what you may or may not have been looking at in the nanophysics. So there we're starting to look at some of the theory of density functional theory. Hopefully those words sort of make sense now. So what I want just to sort of show you, and I'll put up a couple of example files and so on, is how to run density functional calculations in CP2K. Then we can sort of compare and contrast a little bit of density functional theory with classical molecular dynamics that we've done before, and hopefully give a little bit of an overview of things. Right, let's switch over to my thing. So this is a terminal on the Linux Linux kernel that's running on my Windows box. So as ever, please do ask questions, because otherwise I'm just sat here. So if I go to one of the simulations we ran in the past, so this is the water example that I went through. So we had this sort of global section where we specified the project and the system and the run type. And the run type, if you remember, sort of controlled what we did with the overall simulation. And our run type up to now has basically always been molecular dynamics. If we look for the sections, we find this motion section. So there's this idea, if you think back even back to the first lecture we did in molecular modelling, that you calculated the forces on the atoms and then you moved them. And if you did that in a sensible way, you'd generate a trajectory that obeyed Newton's equations of motion, or a slightly altered one that sampled from a canonical ensemble, which meant you had a well-defined temperature. And the other thing, you can sort of think back to the very first thing where we had two argon atoms, I guess, coming near to each other. The other thing you can do is have something called GeoOpt, geometry optimization. And then what it does is, if you start higher up in energy, it calculates the forces, which is essentially an energy gradient, and then it moves the different atoms in such a way that you move downhill. So in the case of just two particles in a Lennard-Jones, if you started at some distance, geometry optimization would be taking sort of minimization steps to try and adjust the atomic positions until they were at that sort of central minimum, which is what, 2 to the power 1/6 sigma, whatever. So you'd optimize. If you've got more atoms, you've got more degrees of freedom, more things to move around, but you can optimize. And so as long as you can calculate the energies and consequently the forces on the atoms, you can move them around. Now, the way we've been calculating the energies and forces up to now have been using these classical approximations. So actually, let's get out of the water one, because even this one's a little bit complicated. Let's go to First empty, argon. So if we look at the argon simulation, oh, it's actually a bigger one. So our forces are just, so we're calculating using this classical module, so method to calculate the force. And as you see in this one that's actually got the comments, you use FIST to do molecular mechanics, which is a word for a classical approximation. Quickstep to do electronic structure methods like density functional theory. So the point is here, if we change the method and the method we use to calculate the energy of the system, and then the gradients, the forces on the atoms, how the energy changes as we move the atom nuclei, then we can do the same things that we're doing with the classical simulation, but with a quantum mechanical description of the electrons in the system. And that's what this DFT does. But as well as getting the positions of the atoms like you do in a classical molecular dynamics, you also get the proper electronic structure and the distribution of the energy levels and where the electrons are and so on, which can be very important. It's particularly important if you've got so-called chemical reactivity happening, if there is a change in the chemistry of the system. Why does this come about? If we go back to the water model, so particularly say the bends and the bonds, strengths, the van der Waals interactions, and particularly the charges that in the classical model we assumed on the atoms in some of the models. These will all change if there's chemical reaction. And the big problem with a classical molecular dynamics simulation is you're basically baking that in. You're assuming that your model describes a certain configuration of the system, like water molecules whole. If they want to dissociate to give you hydroxide ions and protons, then you can't do that using a classical simulation. You've baked it in. So if we want to run a density functional theory, we're going to run something that looks rather similar. Why am I not able to paste into here? Fine. I've reinstalled this, I think. Okay, hacks. Let's change this. I still can't paste this either, can I? First. Right, we'll just have to do it from scratch. Okay, we can do it like this, can't we? Sorry about this. My setup's got broken, which I could do without. My downloads. This is what I was doing. I'm copying it in. I'm downloading it on Windows and then copy. Right. Oh, for sake. Right. Apologies for that. So now I've got a new input file, CP2K, but this one is for a hydrogen molecule. So you can see that it's got 2 hydrogen atoms and they're separated by 1 angstrom, which is round about the equilibrium distance for 2 hydrogen atoms. It's in a cell, so this bit basically looks the same as a classical simulation. There's an extra bit here that I will talk about another time. We'll touch on it in nanophysics experimental theory. So we need to give it some technical settings for how it's going to solve the Kohn-Sham equations, which are this density function theory equivalent of the Schrödinger equation. So there's a couple of things we've got to provide it, which is tells it how we're going to treat the actual nucleus, how that will interact with the electrons. There's some subtleties there, and it will also give us a so-called basis set, which is what's used to convert from Schrödinger equation, which is an infinite dynamic Kohn-Sham equations, into a set of linear algebra problems. So we don't need to worry about that for now. And I can give it run type energy. And this time in the force evaluation section, I've now got that the method is this quick step method, this density functional method. Now, let's try running this, let's see what we get. We've got some stuff from before, but now it tells us we're doing a density functional calculation. Lots of technical details that we don't need to know. And then we get this sort of range stuff here, self-consistent field wave function optimization. Again, this is stuff we'll go into in more detail on Friday. It's sort of slightly later in those series of lectures than we got to last time. So this, you may have got to this Hohenberg-Kohn theorems, which tell you that the energy of the systems are unique functional of the electron density. So to find this minimum, this well-defined minimum energy, which is the ground state electron density, you've got to solve in this Kohn-Sham method. You've got to solve a nonlinear eigenvalue problem to obtain a so-called self-consistent, which is essentially the minimum, this self-consistent distribution of electrons, self-consistent field coming from the electrons that defines the ground state of the system. And what you do is you make a guess at the electronic structure of the system. So you start with perhaps an electron density that's similar to around an atom, which is a slightly simpler problem than this complex molecular one. You solve that, you take an initial guess, which is some sort of combination of the atomic densities, and then you adjust the electronic densities until you find this electronic minimum. And here you can see the total energy of the system is decreasing until it gets to this number, and there's some bits telling us about convergence. We won't go into exactly what this means, but there in so-called 7 cycles it goes through and it finds a minimum energy. And there's a little bit of detail about the different terms in the Hamiltonian. So we've got things like electron-electron interactions that are described by the density functional. There's in the electron nuclei or effective nuclear interaction, and other things like that you can break things down into. So that gives us, I did an energy calculation, so it calculated the energy of the atoms at that location. Just as a sort of example, we can actually change our run type to EO_opt, and it will try and optimize I'm having a sorry, I really didn't sleep very well last night at all. Fast asleep. Now, if I look at my file, it says it's starting to do a geometry optimization. This is the thing where things get a little bit weird. So it does the same thing. It takes a guess at the electronic density, and then it finds the best location for the electrons. Then you can try thinking about how the energy will change if we move an atom. So we can work out the forces on the atoms, shift them. And then we've got to solve a new problem, find a new best location for the electrons, new forces. Yeah, so Ian said, what is the best location of the electrons based on? So this is that minimization problem where we find the minimum energy of the system, which is based on the electronic density that gives the minimum energy of the system. Now the technical details of how we do that get a little bit complicated, and we'll talk about that a bit more on Friday. It will start to be addressed in the lecture series that we linked to on last Friday's nanophysics. But So what it does in this case is it calculates the electron density for a hydrogen atom. I mean, these are actually known, you could tabulate it, but it's actually possible because you've got spherical symmetry and you're just working with an atom, you can actually solve the equations more easily and you can work out what the ideal density around an atom is. And then you can make a new guess for the combined hydrogen molecular system of just the unperturbed density of the first one plus the unperturbed density of the second one, and just start with that as a condition. Of course, when if they're in a situation where they're closer to each other, then the densities will adjust to feel the other atom, and that's what it's doing here when it's moving that down. And so for a given couple of locations of the atoms, it minimizes the energy of the system with respect to where the electrons are, and that's what it's doing here in this wave function optimization. So it's finding a best set of so-called cone-sham orbitals that minimize the thing, and as we'll see again on Friday, these cone-sham orbitals define what the electron density is. So for now, it's sufficient just to know that this is the electronic structure optimization bit, and it's finding the best position for the electrons. So we've put our atoms, we remember, at a particular location where they're 1 angstrom apart. So the story is we've started them 1 angstrom apart. We've calculated the best density for each of the atoms individually. We've got a new density, which is essentially the sum of those two atomic densities. Then we've switched on the full density functional method for the whole combined system. And then we've seen how the electron density wants to adjust based on the two atoms being talking to each other, interacting. And the electronic energy has been minimized in this configuration. Now this has just minimized the energy of the system at the particular position of the atoms when they're 1 angstrom apart. If I do this geometry optimization, what I'm trying to do is to minimize the energy of the combined system. So now I've put the electrons in their best location for this initial starting position of the ions. I'm going to move the ions in such a way that I still minimize the energy of the combined system. So it makes another step. Actually, the energy's gone up, I think, this time, so it's made a bad energy guess. And what it's doing is it's adjusting the positions of the atoms. Now I can see the electron density is, the energy of the combined system is decreasing. I think there's some settings that are very inaccurate in this. It's basically a test calculation rather than a real one. So there are some sort of parameters and stuff that go into it, but they're more like a recipe than, so a bit like the force field for classical calculation, but they're more to do with the technical solution of the set of equations rather than actually defining the Hamiltonian of the system. And so after several steps, there's definitely a bit of noise in the system, otherwise it would have optimized more quickly. I get total energy. I look at the energy of the system. I can see that it started out just one initial thing. First step, it made a bad guess at where to move, but then it proceeded pretty smoothly downhill. If you see that, you can see that the energy is proceeding down, and so in the end it finds the lowest energy of the combined system. I just realised I didn't actually share my screen full screen, but I guess if you pin me, you can see that. If I look at the XYZ file, I can see that the two atoms started essentially 1 angstrom apart, and then they proceed to a configuration that's more or less the same thing. Yeah. So what you're actually doing when you're moving the atoms, once you've found the minimum, so you're doing sort of a double loop, you're doing 2 combined optimization problems. So you put the nuclei at a set distance apart, and then you minimize the energy just with respect to the electronic coordinates, which in this case is the electron density at every point in space around the molecule. So you adjust those densities. You actually do it a slightly different way with Kuhn-Sham theory. That's essentially what you do. You optimize the electron density around the molecule, and that gives you a minimum with respect to the electronic configuration, but still that total energy of the combined system depends on the positions of the nuclei. So once you've, at a given set of positions, optimized the energy with respect to the electrons, you then calculate what the forces are, or what the change in the system energy would be if you move your ions in given directions. And if you've got sufficient if you work through the stuff, you can work out analytically what the well, you can at least calculate it, given that you know the electron density, an approximation for well, the forces on the atoms at that position, and that is the change in the system energy with respect to the ionic coordinates. And so what you do is you then move your ion exactly like you would in a classical calculation. Once you've moved it, you've got to adjust your electron density, so you do another minimization of the electronic configuration at this new position, and then you calculate your new forces on the atoms, so the new gradient of the energy with respect to the different atomic positions. And at the minimum, you should find that the gradients, so the change in energy with respect to the atomic positions, is excluding numerical noise 0. And that's what you're looking for. And if you're doing it correctly, your energy should be going downhill, and you end up at a minimum. So if I go back into this thing, if I at print, I print forces from here. This may crash. I can't remember. Let's do that again. Now I've got the atomic forces, so this would look exactly the same. You know, conceptually, if I was doing just a Lennard-Jones with the two things, I would move the atoms, and then I would calculate the new forces on the on the atoms, move them in such a way that the total force, or the force on each atom, was 0, and that would be this sort of minimum in the Lennard-Jones. This time I'm doing exactly the same, but instead of calculating using a Lennard-Jones potential, I solve the density functional problem for the electrons to work out the energy of the system in that position. Then I work out the gradients, the forces on each atom. So how the energy of the combined system would move with respect to the position of the atom. And I optimize that in the same way that I would with a classical one. So you can see at this final step that the atomic forces are the X and the Z, the Y and the Z forces are actually 0, and the forces in the X directions are close to 0 as well. You can actually see that there is some numerical noise because the sum of the forces is not 0. So if you know Newton's equations were fully being obeyed here, then I would get that. Let's just get a couple more things printed out. Let's print out the electron density, and something again we'll talk about later. We'll print out our eigenstates of the system R. So that, so in that 0.000364 is numerical noise. Yes, so it is. We still have a Hamiltonian. So the density functional defines a Hamiltonian for the system, and energy is a function of these electron coordinates and nuclear coordinates. And you minimize the Hamiltonian energy to find the thing. The minimum energy of the system. What I added in was something to print out the electron density and the actual molecular orbitals, the energy levels of the system. I will just do this for the initial state, so I'll just do it. Typo. Have I done this wrong? I put this bit in the wrong place. So this print bit needs to go into the density functional. It's one of those that you can sort of, after a while, there's a logic there. So the print section, the forces, it's in the outer force evaluation section. To get the electron density, for instance, it's got to be inside the density functional theory section, because if you're doing a molecular mechanics model, then you wouldn't have that necessarily. If we try it again, I should get a couple of files. So copy start cube. See. Now I will go to the downloads file and I can look at the electron density. So the so I've just opened up VMD. Got my hydrogen atoms. If we wanted, I would draw. What? There's a peculiarity in VMD because it was designed for biosimulations where it doesn't draw bonds between hydrogen atoms because normally they're close contacts and you don't want to draw hydrogen-hydrogen ones. So, okay, so well, I won't draw in the bond, but that's the situation you get from the classical thing. But now I can change this. I can change it to an so-called isosurface. So just the isosurface. So I need to pick a slightly different isosurface. Okay, I was a bit silly with how I positioned my atom. And now you can actually see that there is a box. I've got this periodic repetition of the system. And if I pick a given periodic replica, rather than doing that, it'll be easier for me to center my atom in the box. But where you position the atom doesn't change the actual calculation. It just makes it a little bit easier to visualize things. If I just change my box to 10, 10, 10, put my first one at 4.5, 5, 5. Run it again. If I load this in. Well, I've got my atoms again. If I add in my isosurface, let's make it. Oh no, let's make it. I can make this transparent. So there I've got my electron density around the two molecules. So if it was just a hydrogen atom, I'd get a spherical electron density around it. But now you can see it's this sort of ellipsoid where there's been some increase in electron density in this area between the and you may remember some discussions back to tight binding that we've reduced the kinetic energy of the electrons because now they've got the ability to move around in a wider area, which means that the curvature, which is connected, so the second derivative of the electron positions, is reduced because it's not dropping off away from the atoms, but it's got this increased sort of freedom to move. So you've reduced the kinetic energy and you've actually got a binding of the system, and which is something we can calculate in a second. We've got those, and this is the electron density, and we'll again on Friday we'll discuss this in more details, but it comes from the sum of the squares of the wave functions of the wave functions of the individual electrons. So density functional behaves a bit like an independent electron. So if I load in a new molecule, I also got two wave functions. So I've got another wave function here. So one of the wave functions for one of the atoms. If I isosurface, it will look not that dissimilar. This looks a bit ugly because the settings are a little bit crude, so that the number of data points we've got to actually plot this electron density is a little bit low. So this is actually a picture of the individual molecular orbital, the individual electron state, and the electron density comes from sort of the square of this thing. So if we have a look, we turn this on. So we've got the electron density, and that's coming from a sort of a square of this this function here. You can actually go a little bit further. So that's the first ground state. We can get other solutions to the Schrödinger equation or Kuhn-Sham equations that correspond to higher unoccupied energy levels in the system that, for instance, an electron scattering off the molecule would scatter into. It might just be worth doing that. So look at the if I added add in 5 more see if that works. I'll stop in a second. But this is the ground state of the electrons. It's sort of symmetric. It's the two wave functions in phase. But if I load in instead, instead of this one, if I load in What did I do wrong there? Why is it not produced these extra states? Yeah, so let's change. So just a technical setting. I think. Someone's changed something. Right, and now if I load in second orbital, get my atoms back, then my isosurface. So here I've drawn an isosurface with a value of minus 0.1. If I create a new isosurface with a value of 0.1 positive, colour it blue, then this second state, this higher excited state, is an antiphase combination of the wave function on the two individual hydrogen atoms. So you get plus minus, and that results in a reduction in the electron density between the two atoms, and that means that kinetic energy ends up increasing. You can see that there's a that there isn't wave function here. Once you square it, there will be a reduction in densities that come about there. And the last thing, I actually end up giving quite a long waffle, I'm afraid. Sorry. You see, it actually gives these eigenvalues of the individual energy levels. So there's one energy level which can allow two electrons can occupy at a binding energy of minus 0.3 atomic units, which is atomic units 27.2 electron volts. And then there's unoccupied levels, higher energy levels, higher up, and so to optically absorb. So if you like, that difference between that energy and that energy is which is given as the HOMO-LUMO gap, which is kind of the band gap for a molecule, like a slightly different name, is 9 electron volts. So it requires a lot of energy, sort of hard UV, to actually carry out that sort of transition. Okay. I was trying to sort of whiz through it. There was basically only a couple of points that really wanted you to take on board for this session. The idea you could calculate the energy and forces as a function of the atomic positions, but using a density functional description that included the electronic structure, instead of just saying, oh, it's a Lennard-Jones, or it's a Lennard-Jones and some electrostatic interactions or something. So we can include the electronic structure properly. And then when you're practically carrying it out, it's sort of a double minimization. For each position of the atoms, you find the best location of the electrons. Then you calculate the forces on the ions given that configuration, move them, then find the new electronic minimum, then find new forces, and you sort of do this double thing. If you wanted to do molecular dynamics, you could equally well do that. So instead of just minimizing it, you let the atoms move, and the electron density adjusts with the ions all the time. So that way you can actually study catalytic reactions, and there's quite a lot of stuff in astrochemistry, molecules absorbing onto dust in little silicon particles, often in the cosmos, things like that. Lots of things you can do. Once you've got the electronic structure, you can work out where the transition energies would be to absorb light. You can start work with Matt Booth on sort of looking at particles and how they would absorb light, where defect levels would be, all this type of thing. So that's some stuff that we will start talking about a little bit more on Friday in nanophysics. What I'm going to do is I'm going to stop talking now, because I talked for much longer than I expected.